That's compared with the covariance of singularities. If our covariance goes to 0 in the Big Bang, it goes to infinity in the singularities. And why does it lose? Is it quantum gravity? If it's quantum gravity, it must be a very peculiar time asymmetrical theory. But for a long time, I think it's myself. Can we move to the next slide? I don't want to go into this because it's not really the argument I want to go for. But I think if we want to study quantum gravity, we have to understand how it is that the principle of equivalence, this picture describes the principle of equivalence, as emphasized by Galileo. Imagine a big rock and a little rock being dropped from the tower. If this, according to the principle of equivalence, they will drop together. In the bottom picture, you would see an astronaut and the 2001 race station. And even though the Earth is right there, the astronaut does not feel the gravitational field of the Earth. It only calculates the principle of equivalence. Now, in the next slide, I tried to show the principle of equivalence. I won't go into this in detail. It shows that the principle of equivalence is in conflict with the principle of superposition. The bottom picture, part of the picture shows the two bodies in superposition, and the blue one and the grey one, brown one are supposed to be in superposition. And you can show from the argument I gave, when you try to bring the superposition principle, the equivalence principle. That means that a Galileo is free-forming equivalent to a gravitational field. You get rid of it by falling freely. And this work, we're in trouble with. I don't want to go into the argument because it's not where I was taken. This argument really showed me that there is something funny about quantum gravity. It's not going to be an ordinary quantum mechanics theory. It's going to involve the wave function in some way which we do not understand. So I want to move on to the next slide because I've given up on that. I want to think about something else. I spent a little time studying conformability, which is a useful trick. The way of squashing down infinity to make it look like something nice and smooth. And in this picture, I've moved down the infinity in the future to a nice smooth number. It's using the trick. Can I have the next slide, please? The next slide, I showed you how Escher used this nice trick. This is a conformal map where infinity of this particular geometry, for hyperbolic, don't worry about the geometry. The point is that in this picture, using the Beltrami transformation, where you can formally map down infinity between smooth boundaries. And it illustrates that conformal, but you see, these fish creatures, their eyes remain circular, no matter how close to the boundary you get. So it squashes down in a conformably nice way, which gives you a nice boundary to study. The boundary is smooth, and you can study it. Can I move to the next picture, please? I'm trying to show now what conformal means in space-time. Here we have the light cones or plot cones, which I talked about before. They don't quite describe the whole of the metric. They describe 9 out of the 10 components of the metric. When I say 9, it's really the 9 independent ratios of the 10 components of the metric. Now, what is the 10th component? The 10th component is the scale. And in this picture, I've shown you how the scale works. I have two different observers moving at different speeds, the red one and the blue one. And I'm looking at two famous formulae of 20th century physics. E equals mc squared, that's the top formula. Einstein's formula, which tells you that energy and mass are equivalent, C being a constant. The lower formula is Planck's formula. Planck formula is energy and frequency. E equals h nu or f. Nu or f are the frequency, h again the constant, and this tells you that energy and frequency. When you put the two together, it tells you that mass and frequency are equivalent. So if you have a mass, it's like a clock. So the clock, a mass determines the scale which gives you clocks. Converse to this, if you do not have mass, if you have a situation where mass is absent, then you do not have clocks. You only have the null curves. You don't know how to talk about distances, times. You don't have times and distances. You only have the null curve. Can I move to the next slide, please? This is going back into our picture now. If you simply have null curves, then you could squash down infinity, like in the Escher picture. When you have a positive cosmological constant for dark energies, is what it these days, positive cosmological constant, then this infinity is space-like. It's very nice for it to be space-like. I used to study it when we didn't have a cosmological constant, and we worked out these things with colleagues, people looked at gravitational radiation. The story is a bit different when you have a cosmological constant, because you have space-like matter. And you have a picture which, now the picture also is the, if you see in a remote future, that's pretty where all the mass is from, first you have filter, therefore you talk about infinity without any mass. That's a good approximation of what you can do in the remote future. The Big Bang also, following up on a suggestion due to my then graduate student Paul Todd, suggested another way of describing, not talking about the particle directly, but saying, space-time, we stretch out the Big Bang that license to. So there are two conformal tricks I'm using. The future is squashing down infinity, which as long as you have massless things in the remote future you can do. The Big Bang, you can stretch out in the same sort of way, but as long as you have, for a different reason, you can talk about massless things being dominant, because the temperature gets so high that the particles are moving around so fast that their mass becomes irrelevant, because the energy of motion dominates their rest mass, and so they might as well be massless. So in the two ends, for quite different reasons, the physics is dominated by massless physics. So this picture makes sense, not only physically, metrically, but also physically. It also makes sense if, well, can we move back to the previous picture for a moment? Can we move back? Thank you. I just wanted to say it makes physical sense also, not just mental sense, because we might say, well, it's very cold and rarefied, but when you squash down, the coldness becomes hotter and hotter. It's very hot and dense. When you stretch out, it gets hot and the density becomes smaller and smaller, and so they do become very similar to each other. They're not only similar, this picture is not outrageous, okay? This similar looking Big Bang in the remote future, if you consider the conformity. So what is outrageous is, can we move now to the next picture? This is like picture of conformal cyclic cosmology, that the Big Bang is in fact a continuation of the remote future of a previous eon. This previous, the brown one is the eon prime ours, the blue one is our eon, the green one is an eon succeeding ours. Our remote future, according to the scheme, will be the Big Bang of a following eon. It's hard to get your minds around to this idea, but we're not used to thinking conformally. See, when the Big Bang disappears because in the Big Bang it disappears because the temperatures are so big and the mass becomes irrelevant. In the remote future, because it's mainly photons, I have to argue also for reasons from general arguments that the mass ought to declare away in the remote future. You don't want to go into that. But there are reasons for thinking that it's not outrageous. In the remote future, you could lose the mass as well. Now, the argument is this. I used to talk about this thing, and I would look at these lectures like this, and I would be confident that nobody ever would be able to prove me wrong. However, that's the thing, well, there are ways of proving me wrong. Can I move to the next slide, please? You see, signals can get across. Here, in this picture I'm showing, the horizontal or curvy line represents the crossover between one eon and the next eon. I'm imagining this is the previous eon, the prior one, but this our eon is the post beyond that crossover. So signals can get it. If you have low enough electromagnetic signals that could get across, things like magnetic fields and things could get across, it's an interesting question to know what would happen with that. Another signal which could get across would be gravitational wave signal. I'm going to talk about something else we can get across shortly, but I'll come to that later. But gravitational wave signals could get across. In the next slide, I want to indicate the sort of thing I'm talking about. You see the red plane represents the crossover between the previous eon and our eon. The top picture is now looking back, that's the orange. In the previous eon, we have a collision between supermassive black holes in a galactic cluster. In a galactic cluster, you will have lots of collisions between supermassive black holes. They will happen many times, bang, bang, bang. And these will produce gravitational wave signals, which people can see. Our meeting colleague, Martin Guzman, looked at this in a particular way, looking at low variance rings. So he looked at rings which are low variance, and if you have several of them, you would find concentric such rings. And he did find many of these rings. So can we move over to the next slide? I want to show you. This is a very remarkable picture taken from the Planck satellite. These points, each individual point represents a center of at least 3 rings with the same center, which are low variance. And they're picked out from the fact of the low variance. Now what's remarkable here, they're very clumped. Not just that, the clumps not just in distribution, but also in color. Now what does the color mean? They're singled out from the low variance, not from the actual average temperature. The temperature now here, the red ones, actually they are the lower temperature, and don't worry about that too much. But the fact is that they're red, and this means for a reason which I won't go into, they have to be distant. The blue ones are not so distant, these are relatively close. The fact that they're clumped by color means they're clumped by distance as well. What's very remarkable goes against the current view that on a big enough scale, the universe should be really small. That doesn't seem to be true. These rings, from these observations, and nobody has predicted this, it's not going to be, we certainly do see this clumping feature in the Planck satellite data, no variance ring. These 3 of them are the same center, and they're clumped not just where they are in the sky, but in their temperature, which in theory would be the red ones are very ones outside our particle horizon, the ones which are inside the particle horizon. You see outside the particle movement in the steam because the steam allows you to do that. Let me talk about some other signals. I should say that my Polish colleagues, Krzysztof Meissner, Paweł Borowski, and in some most recent signals which I talked about that, first of all, they see signals like these using a different type of analysis. They also saw confidence level of, I think, 99.4 confidence level these signals dependent. Let me talk about something else. This is a paper published for a year ago. You notice the Royal Astronomical Society monthly notices. Can we have the next slide, please? So this next slide is what we're looking at. This is the walking evaporating of black holes. You see, in the remote future, you will have black holes, they will collapse to finally they will evaporate away, open evaporation. This radiation may take something like 10 to the power 100 years, maybe more, very, very long time, and they will disappear in a pop. However, it happens so late that this will be squashed up at this one point. Can we have the next slide, please? This is a picture taken from the monthly notices of the Royal Astronomical Society, given by myself, Christoph Meisner, Pavel Nerosky, Daniel, and the computer analysis. And what we found is, with a 99.98% confidence level, certain feature was observed to be there. What we saw in these spots in the sky, this is what we see, at a sort of scale of about 8 times over the moon. So you have to imagine this is the intensity going up in the little town, as you know, like a sort of spot in the sky. What do we claim it is? Okay, now this is what we claim we're seeing. This horizontal line at the bottom would represent the crossover from the previous eon to ours. This vertical line represents the galactic cluster. It starts to evaporate away, and in this picture we come very close to this crossover. Finally, the Hawking evaporation takes place. Everything is squashed into this little point. It comes through into the next eon, so this is our eon above that point, and it would be spread out. You wouldn't see anything, because you don't see anything until 380,000 years after the Big Bang. According to our scheme, there's some little argument about along the states. What we're trying to see is, and this spreads out 8 times diameter of the moon, which is this diameter you're seeing here. And what you see is a spot. So according to the theory, this will get spread out. Exactly how far this is slightly distributed. It might be slightly less than this, or it might be this. But what we actually see in the data is 8 times the diameter of the moon, which is this diameter indicated here. So what we see is the signal at the top, the signal is spread out, at that level, we see a 99.98% confidence level that these spots are actually there. I don't know a theory which predicts these spots. I should also say that they relate to the volcano in 2 slides prior to this. I think it was 1 slide prior to this. If we could go back to that one. 2 slides, the one before that. Yes, this one. If you look at the data in these spots, and you look at the 6 strongest spots in the paper that we see in the monthly notices, the 6 strongest points, in order for them to be Hawking points, it would have to be green points. I could go into that once something wants to go. It would have to be green points in this scheme. And if you look at the 6 strongest points, then the 5 strongest points in the W map, the 5 strongest points in the flag data, we find them also at the same places in the W map, exactly the same spots. If you look at the 6th spot, they're almost as strong as the W map. You look back at the flag data, and that's there too. Those 6 strongest points, I looked for them in the Barney data. Are they there? They would have to be green points. I would have to explain why they have to be green points. They would have to be green in the color coding. The 3 of these 6 points are to be found exactly in the same spots in this picture too. That's pretty good, I think. I can't remember where they are exactly now. In this picture you can find even the 6 spots are you can have to look at these 2, which are within the pixel, which is quite remarkable. So they seem to be there. That needs explanation. I haven't seen any explanation. Not many people who repeated this. There was another, I've not even seen anything coming on the actual paper that was published in the monthly notice. Actually, what's done this. That's something to let me know. Anyway, that's the end of my talk. Thank you very much.
Thank you very much, Professor Penrose. Roger, do you mind to take some questions?
I'm happy to answer questions.
Right. We're really out of time. We have time for one question. Yes, Bhakto.
No, well, I wouldn't say it's one of the bases of it. It is in a sense, yes, because the booking evaporation is where most of the entropy goes. Yeah.
Not be the entire thing. Right, the evaporation would not be the most important thing perhaps.
Yes. The answer to your question is it doesn't make any difference. You see, the arguments which I gave, I talked about it in terms of Hawking evaporation, but it would not make any difference to the picture if that did not happen. So it does not depend on the Hawking evaporation. All you need is the energy concentrated in a galactic cluster. And that energy comes through whatever the form is. It would not make any difference to my picture. So you could have the black hole stabilizing, you could have anything you like. It makes no difference.
Thank you very much.
Yes, thank you.
Once again, Jonathan, thank you very much. I am sorry we have to go up so early in the morning. Thank you ever so much. Thank you. This talk is over. Now I hand over to Krishnan Srinivasan to share the next session.